Howdy and welcome back. This is the third in a series of videos showing you how to set up and work with the ZED X cameras with ROS 2. Check out the last two videos if you want to see the unboxing of the ZED X camera with a video guide for how to install the GMSL2 capture card into the Jetson developer kit. As well as the last video where we set up the Stereolabs and ZED X SDKs. The links to those videos will be in the description below along with any other relevant links from this video. So in this video, we're going to be setting up ROS 2 with the Jetson Orion AGX developer kit and start working the ZED X camera in a ROS 2 environment. Alrighty, well, let's get started here. So first off, we need to install ROS 2. However, unfortunately, the Jetson boards have always been crazy behind in terms of the operating system support, so these are actually still on 2004, which aligns with ROS 2 Foxy. However, because this is so far out of date, Foxy is actually already end of life. So instead, we install something a bit more modern, so something like ROS 2 Humble. So we can get away with this using NVIDIA's provided Docker containers, but I think it's actually a valuable exercise to show you how to install ROS 2 from source, because it's really not all that hard, so you can work on it with a bare metal environment if you choose. Plus, I don't want to scare anyone away in these particular tutorials with using Docker, so I want to get away with the minimum default tool set as much as reasonably possible. However, if you're sufficiently comfortable with the NVIDIA Docker containers, you're certainly more than welcome to compile those with your flavor of the L4T and Jetpack instead. So, alrighty, let's get started with the default install. So we're going to just go here and look at the tutorial here for installing the Humble ROS 2 Humble based on just the taking out the source code. So you can see some general requirements, although we're going to ignore almost all of that and just get started with the instructions here. So the first thing we're going to do here is just do some prerequisites needed to set up the rest of the system. These are things that I've already done here, so these things should all go pretty fast, although these particular first few steps should also be fast on your side as well. Sweet. So just run these commands real quick here, just to set everything up, and we should be good to go. All right, next we want to do here is set up the ROS 2 app repository. So because we're going to be using this on 2004, not 2204, we're not going to be able to just do apt-get install all of our different packages to get the binary installations. We're going to have to build everything from source. However, there are some useful things that we need to actually grab here in order to do the rest of the system. So things like colcon and the build systems that are required to actually build ROS 2 itself. So we're still going to want to run these in order to grab the ROS build tools. We'll see here in just a moment. So again, just copy paste all of these commands and you should be good to go. They're all pretty straightforward. No need to really pay too much attention here to the actual what's happening here for the purposes of this tutorial. Then again, so we want to actually do the installation process of some of the key things. That's what we're getting from this command here. So the first thing here, really notice this ROS dev tools package. So this is a meta package containing things like amen and colcon and all the kind of stuff we're going to need to do later. So this is very important to actually we do this step, even though we can't actually use the binaries themselves. Alrighty, and then finally do some Python stuff. So again, we're using 2004, so make sure you take the 2004 tab and go ahead and copy paste that into your terminal to install these packages. Again, I've already done these steps, so this is pretty quick. But again, these should be pretty quick on your system as well. These are relatively small packages. Alrighty, well that's all the prerequisites in place that we need before we can get to actually installing the ROS 2 source code itself. So what we're going to want to do here is actually now create a directory that we can stick our source builds into. So I generally put this in my documents just because I like that. You can see here that I actually already have a ROS 2 workspace and a ZED workspace installed, so that way we don't have to sit here and watch me for the next hour compiling ROS 2. But once we get to that step, we can take that step forward. But so let's create our workspace. We want to go ahead and install things. So we're going to make a directory -p so we can do recursive. And let's call this, I don't know, like ROS 2 Humble. Oops, didn't mean to copy that. And then we'll create the source directory. So let's go ahead and go into that source directory, which is empty, right? We just created this thing. And so we want to actually put in all the different packages we want to install. So here, the instructions here are just basically just to grab from GitHub the ROS repos file, which you certainly do, which will give you the latest and greatest and whatever it is that the Humble has to offer. But it is useful to mention here that actually in the ROS 2/ROS 2 releases, that's where all these things are based out of. So you can go ahead and pick whatever ROS distribution you like at this point. Or different patch versions of whatever it is you're interested in. So we can go to the assets here. That will show you all the different things we have available to us. If we actually were working on 2204, there actually are just a tar of binaries that we could potentially install. So instead of going apt-get install for all that kind of stuff, we could just grab this tar file and then untar it and install those Debians. But again, since we're actually working on a different operating system, we actually have to do that source build instead. So unfortunately, we can't just grab the pre-built binaries. Although that would be nice. So instead, we're going to grab what's referred to here as the source code. Although this is actually a tar file of the ROS 2 repos file for this particular release. So we can go ahead and download that, and let's take a look at the file. So this is again here's just your tar file. And inside this, you can see this ROS2 repos file. So let's just open this up just to take a look at it for just a few minutes here. So you can see here that basically we have a YAML formatting, and we have a bunch of different packages. So you can see, you know, ROSbag, and I don't know what else here, RCL, grabbing XML vendors, grabbing RQT, you know, all this good stuff, you know, fast DDS, all the kind of stuff that's needed for a core ROS2 build of things. So essentially what we're going to be using is a tool that's going to parse this file, and then it's going to grab each of these different repositories at their particular URLs, at their particular version numbers, and then clone those into the directory that we set it at. And then at that point forward, then we can then build them. So this is just a really nice way to put a version control of a bunch of different stuff all in one individual file. All right, so let's extract this file because we want to actually use this somewhere else. So we're going to go to our ROS2 humble, into our source, and we're going to extract it there. And I don't need to see it. All right, so let's look, and we can see that, hey, here's our ROS2 repos file. So this is the same kind of thing. If you want to just grab it from here instead, you're certainly welcome to do so. And then we're going to use this VCS tool, and this is actually what's going to be used to actually download things. So let's just parse this command real quick here. So we actually aren't going to be grabbing it from the internet. We're going to be grabbing our local version of it, which is right here. So it's still called ROS2 repos file. And then rather than the source directory, since we're already in source here, we're going to just change it to a period for our current directory. And then we're going to hit enter. And so what this is going to do is VCS is going to basically start going through the different version control systems that each of the different repositories are under. These are all Git repositories, so they're all, you know, basically on GitHub, I think, maybe a couple are on GitLab. I don't know off the top of my head. And it's then going to clone the version of each of those the branches that respond to the tag that is our particular release. So you can see here we grabbed it from Humble patch 4. So this is the 4th release of all the different updates on the core Humble kind of system. And we can check here if we just make a new terminal that's in here, and we can see that, hey, there's some stuff being populated here. So you can go OSRF, and we can see that, hey, we got some tools in here being installed, you know, ROS tooling, got a couple of these tools installed. And so over time, basically, we're going to see that this is being actively populated by the VCS tool as we're installing the system. All right, and more or less, that's essentially all we need to do on this particular page. So, you know, you can set up we can set up ROS step here as well while we're doing this. And okay, there we go. So we're all done. So this basically prints out all these different outputs for you, basically showing all the different versions. Although you can just ignore it for now. So let's go ahead and run the last few commands here. So while ROS step is not going to be very helpful for us in the situation of trying to install Debian ROS packages, it is still going to be useful to us for the ability to install Debians that are not ROS packages. So if there are certain libraries that ROS packages depend upon that are not themselves ROS packages, then ROS step can still be helpful to us in order to install those guys, so you don't have to manually just do all this all the time. So ROS step init is just going to initialize it. Update is going to basically grab all of these different source files and make sure we have the most up-to-date set of information about all the different packages we have available and our particular distribution. And then finally here, this ROS step install step is then going to install anything we possibly can based on this. So if we parse this command just real quick here, so essentially we're doing ROS step, which is the tool, install, so we want to install a bunch of stuff from paths source. So that is going to be the path of where all the packages are, where it's going to parse the package XML files to see what kinds of things we might need to install. So rather than source, it's going to be period because our current directory, because we are in the source directory currently. Ignore sources, which is going to be just ignoring to install versions of things we have currently in our source directory tree, so that we're not basically installing things we're going to be building later anyway. Dash yes, so we make sure we just automatically do it, and then skipping some keys of things that we don't particularly want to deal with in this situation. So cool, we ran it, things were all good for us, so that we didn't run any particular issues. So from this point, this actually is pretty much it. That is all the prerequisites needed. We got all the source code we need to build ROS2, so we can just go ahead and CD back down to our core workspace directory, and we should be good to go. However, there are a couple of quirks here because we're working on the Jetson boards and we're running a distribution which is not meant for this particular distribution, particularly with some Python issues. So I ran into a couple issues when I was building, and I found these as suitable alternatives for how to fix these issues. So if you run these two commands were added into this particular pull request, then we were able to actually update the Python version of things so that when we later try to install, we're using the right version of Python 3, the system that are attached to Humble expect. So we go sudo copy paste for this alternatives, Python, poof, you should be good to go. Again, we want to do app purge and download a particular version of Python 3 we want to be working with. Again, I've already done this, so it should be very fast, and poof, we're good to go. So that's everything we need to do just to set up our source build. And from this point, we can just go, as you can see down here where it says up here where it basically says, hey, time to symlink install Colcon build. So as you can see here, we're starting to build our workspace. There's 344 packages, so it does take about 1 hour to build this entire thing on your Jetson Orion AJAX developer kit. Go get a coffee, talk to your colleagues, do this before you leave for the afternoon, and you should be good to go in about 55 minutes, which is as long as mine took to build. So that we don't have to wait here for the next hour beforehand, I'm just going to go ahead and kill this because I've already done this for you. So if you go back to our documents page, you can see that there's this ROS2 workspace. And if we go into this ROS2 workspace, we can see that there's already installed build log space because I've already built this. I can show this to you that if we try doing Colcon build, that it's just gonna blitz through everything pretty quickly here because this has already been built and we're ready, good to go. So at this point, so we now have this install that we can work with here, and we can prove that it works. Let's go to source this workspace. So we have now ROS2 sourced, and then we can just execute whatever the talker node, and then we can open a new terminal again, source this workspace, and now run the listener. And there you go. You should see that things are being communicated. So we've now installed ROS2 Humble through these instructions, and we should be good to go now to messing out with the ZED cameras. So with that, we can now close our Humble install. We can now close our release, and we can now remove this this patch that we had to do for Python 3. So now what we're going to be working with here is now this getting started with ROS2 and ZED. So this is basically just a tutorial to explain to you how it is that you can be working with the ROS2 driver of the ZED cameras. Some prerequisites here, we can just ignore that, and we can go over now to these set of instructions about how to build and install it. So we can now use our ROS2 workspace and instead create this a new workspace. Let's call it ZED2 workspace, since I already have a ZED workspace that we can be using after, so we don't have to wait for the building. We can let's go into this ZED2 workspace, so source, and we can now clone it out the Stereolabs wrapper that we're going to want to be utilizing here. And now we can see that there you go. There's the ZED driver. It's gonna want to make you do ROS install and some other stuff, but we don't need to be doing that since we can't actually install the Debian dependencies here, unfortunately, because we're not running on 2204 like Humble was expecting. We're on 2004, so we're gonna have to manually actually deal with these dependencies. So for my previous build, I actually already found out what these dependencies are by going through the source code. So if we go to the ZED components, and then we go into the CMake file, we can see the list of dependencies here. So I cross-listed this to what is already automatically installed in the ROS2 repos file. And so I've identified here a few different things that we need to manually install or we need to manually clone, so that when we build this ZED2 workspace, that we're getting all the dependencies that are required for the ZED driver, so then the ZED will start working for us. All right, so the first one here is this geographic info. So we're gonna just git clone that guy at the ROS2 branch, and we'll just clone that guy. Then we can close this branch. Then we need to grab this messages package, but again, just git clone at ROS2. Boom. We need to grab angles, which I honestly am not 100% sure why that is not just already part of the ROS2 default install. This is pretty much used by everything. Then we got diagnostics we need to pick up. So git clone diagnostics-b ROS2. Luckily, all these, the default branch for ROS2 is just ROS2, so it's pretty easy to just remember that. We got robot localization, git clone -b ROS2. And then the last one we saw here is Zacro, which also a little confused why it actually isn't part of the default ROS2 install as well. but it's not, so we need to grab that here. So we now see that we have all of the different dependencies that we need to build all the components of the ZED ROS 2 driver. We do need to grab one more package, which for some reason the ZED driver is not properly established as a dependency, probably because it's actually a dependency of robot localization. Since we're not grabbing that from Debian, then its own requirements aren't grabbed from Debian either. So we do need to go sudo apt install this particular package as well, this libgeographic, which contains some information that the knapsack transform and robot localization uses based on geographic information. All right, so now we're good to go with that. We don't need to see the source code here anymore. I've already gone through this for you, so I know which packages that are required. And yeah, so now we can actually build this package. So luckily, because we are separating this from the actual core ROS2 itself, so that in the future we can build on top of that ROS2 repository or that ROS2 workspace with other additional workspaces with new systems, rather than trying to integrate everything in that one giant workspace and then you like recompile and just a huge pain in the ass. So instead, what we do is you typically have an underlay workspace that is your ROS2 core system. So what we're going to do here for the ZED workspace is we're actually going to source our ROS2 install space. So ROS2 workspace / install setup.bash. So that gives us now all the stuff that we've pre-built already from the ROS2 install, and now we have the access to that now when we want to work with the ZED workspace. So we're going to do just the same thing here. Click on build symlink install. And we're gonna let that build. So this is gonna build all these different packages. I think there's like 14 or the 16, I guess. So what's nice about separating this workspace from the previous workspace is that now we have the ability to quash and do a rebuild of our Z2 workspace without having to rebuild an hour's worth of information. And we got different workspaces that can all point back to that same ROS2 humble workspace. If we have different developer branches or we have different kind of projects we're working on, we can all share that same thing without having to have multiple different workspaces, all with ROS2 itself being built every single time, which would become quite unwieldy to deal with. All right, so we don't need to let this sit down and build because I've already actually have a ZED workspace, as probably you guessed here from this ZED workspace that was already here. So we can see that in our source directory, same packages are here. I've already sat down and built this, so I know that this works already. So we can just source that, install that setup.bash. What's really nice about using the underlay and the overlay workspace is that now that if I source this install file in my ZED workspace, part of it's already being cached, that it's also sourcing the install/setup.bash file from the ROS2 version as well. So for just this one command, basically I'm daisy chaining multiple different workspaces together, which is quite convenient. Sweet. All right, so now that we have ROS2 built and sourced, we got the Z2 workspace built and sourced. We're now ready to start the node. So there's some instructions about how to set up the Z node. So we can just grab this launch file and just run this guy and see what our output is here. So cool, we're running some launch stuff. There's some interesting outputs from the Z node, and it seems like we're publishing data. So let's go ahead and in a fresh terminal here, let's again source this file, and let's just check out what topics we got here. All right, so we got TF being published by the node, and we got some robot description and join states being published. So let's open now Rviz to see what we can visualize here. So display types just give you all the generic display types, but by topic then gives you actually all the topics you have access to. And yeah, it looks like we're missing some information here. Okay, yeah, sorry about that, folks. Yeah, apparently I forgot to deal with a certain caching issue. So I got things working now again, so we can go ahead and continue. So we got this ROS2 launch, Z wrapper, ZXM launch.py. If you're using just the normal Z camera, you can just use just the ZX, but the ZXM is for the mini. So just go ahead and execute that. And you see we got our launch system going. We've got the camera opening, got the depth information coming in. So now we can just go ahead and check the ROS2 topic list to see what kind of topics we have to work with here. All right, that looks better, doesn't it? Okay, so we got our joint states, we got our robot description. So there's going to be frame information about the different cameras, the IMU and whatnot. We got confidence information with the depth information. We got the depth information itself, disparity map, IMU data, which is really nice. So you can use that for fusion on your central fusion techniques. That is actually hardware synchronized with the left camera, I believe. So that is quite nice and to use all the modern algorithms. We got our left camera. We got the camera info, calibration information, a rectified colored image, which means we're using that calibration information to rectify the image to be proper. We got the IMU transform. Got some more information, different types of camera. We also have this ODOM message, which is quite interesting in these map path images. So what these are is actually, this is the VIO technique that comes built in with the ZED cameras. So this is actually producing odometry, visual inertial odometry, using the stereo camera and the IMU in order to estimate the robot's pose. That map ODOM and that path ODOM and path map, those are then providing tracks in terms of those frames, rather than just providing just the absolute pose. We also got a point cloud, as I hope you expect, pose, which is also going to provide similar information. Instead of being an ODOM message, it's now going to be a pose message containing the VIO solution. We got the right camera and some more RGB information, and then the stereo pairs. And nice that we got an IMU message that gives us the temperature to make sure we're working properly in the proper temperature bands. All right, so now we kind of have a bit of an understanding. We can now go into the Rviz tool. So we can go into by topics, or there you go. We saw all of our topics this time correctly. So I don't know. Let's go to our left image, and let's get a color, because that color is always better. And we got the image. So hey, there I am. And we got the left image here. Let's see. Is this easy to make it kind of just do right here? There we go. Right. So you can see we are our left and right topics. We can visualize here in Rviz pretty easily. Yeah. What else do we got here to work with? So we got the ODOM message. It says it's gonna be the pose. So there's like the pose of the camera perhaps. So let's check out the TF tree. So visualize by type TF. There, yeah. So there you go. So we got these are the TF frames of the actual camera itself. Just because those are a lot of frames. Let's go ahead and just enable only the base frames. So just ignore all the individual cameras. So we're just tracking one particular frame that belongs to the camera itself. So now let's I don't know why not. Let's go grab the right camera again and show that off. So you can see. So now I'm going to be moving the camera, and you can see that the update of the camera frame is moving correspondingly to the motions of the camera I'm giving it. So that ODOM message is kind of annoying. So let's go ahead and just find a different way to visualize that. I think there's also this path version of it. Yeah, it just gives you like a path message version that's been like downsampled. But you can see the orientation is very stable. I'm not sure if you can quite see, but on my side of things, it's responding very, very quickly to the actual motions I'm giving it. All right, we'll just put that guy back down here. Cool. All right, what else do we have to work with here? I mean, depth data, right? I'm working with the depth camera, so let's look at the point cloud information. Point cloud registered. And because there we go. So there's me in a 3D point cloud version. So you can't quite see me waving here. I bet the AGX developer kit trying to visualize this is not having the best frame rate here in the world. So I don't want to show this to you for too long in full 3 dimensions. But there you go. You can see the depth data in Rviz here as well, using a standard point cloud 2 topic that you might be able to ingest in something like Move It 2 or Nav 2 or what have you. And then you can still see that, we're moving this guy around. I think there's another way of visualizing that motion as well. Maybe the pose with covariance. Oh, yeah, there we go. I like that much better. So you got this nice arrow attached to the base frame and a set of covariance information. Yeah, I wish for the purpose of this tutorial, I had a longer cable, or I didn't have this set up to a power supply, and then I could actually move this around the room a bit more to actually get some more data showing this off. But I guess things to do for the next tutorial. But yeah, I think this is a pretty good demonstration of all the different kind of messages you have available to you in the system. So we got a confidence map that also maybe that's we're taking a look at here as well. So there we go as a confidence interval. That's pretty nice. Got depth data, which is the same things we've already seen. The left cameras we've already seen. This pose tracking information. Temperature. I don't know. What does that actually show? What does that show us at Rviz? I actually don't know. I've never displayed temperature in Rviz before. Is it somewhere on the display? You think? Oh yeah, it's like right there. That little blue thing. Oh, okay. Just like depending on how I bet it gets like more red the hotter the camera gets over time. So that's kind of neat. All right, let's just close out the Rviz here. And yeah, one thing to note here that's kind of neat if we go back to the actual the GitHub repository, the wrapper. So that's just using the default parameters, right? I didn't actually change anything about how the system worked, but there are a set of parameter files that contain lots and lots of different configurations that you can utilize with your ZED cameras. So things like saving data sets, there's different video options you can do. These are all things that we saw through in the last video. There's those example utilities under user tools ZED that you can set up the different modes of operation, different gains and exposures. So it looks like you can also do it through the ROS interface here, which is really nice if you don't want to actually use those pre-built applications. Again, setting the different depth modes, you can set like the neural depth, ultra quality, performance, all that kind of good stuff. So it looks like we're using ultra by default here. So good depth quality out of the box, which is good to see. Then so it looks like we've enabled post tracking as we saw, that we had all those different frames we could work with already here by default, which is nice to see as well. So that means that we're pretty much just good to go in terms of if you want to use VIO, just plug it in, run the launch file, and you're good to go. This also publishes out the TF tree of the map and ODOM and stuff. This is something actually that's kind of a quirk that I think that probably I've been talking with Stereo Labs to see if we can get that changed. But by default, it actually is publishing out a full TF tree from map to ODOM to base link to the camera frame itself, even though that the camera driver has no information about what it actually base link is, and no information about map information. It really should just be publishing like an ODOM to like sensor link kind of thing, or a camera ODOM to camera link kind of thing that can be remapped and then fused with the rest of the system as needed. So maybe we can do a little bit of updating there, because out of the box I think this would be a little bit of pain to deal with, but not too much of a hassle to change a few of these parameters and just disable basically the publishing map TF option of things. Got your QoS quality, some other stuff here. You got GNSS Fusion, which is really nice. So if you have an IMU that's publishing out, you can use the VIO. Sorry, if a GPS sensor publishing out, this will actually use the VIO solution with the GNSS to give you a good fix of things. So this could actually be a replacement for robot localization if you're actually using the ZED X camera or the ZED cameras themselves alongside a GPS sensor, which is quite neat. Then we have the mapping parameters. So these are essentially the height map based solution that makes like a mesh of the environment, which is kind of cool to see that we saw in the previous demonstration using the ZFoo tool. Some general sensor information, object detection kind of stuff, body tracking, all these kind of advanced features that this system has to offer you. But yeah, we can go and close that out. I think we're done with that. I don't think there's anything else we need to see here. Yeah, displaying some Rviz data. So there's some nice launch files you can use that come with the system about how to actually visualize the set of data with some pre-built panels that make it look really nice versus the just randomly selecting some random topics like I was doing here. And then it goes over a bit of like all the different topics you have access to and what that information represents. And yeah, so I made pretty much a pretty complete here set of full files. I think the last thing that's kind of cool to mention here is that this actually will work with pre-recorded SVO files, which is the internal Stereo Labs data set. So using some of the tools that are provided in the ZED SDK, you can basically download and record a bunch of information while the cameras are running, either through ROS or not through ROS. If you don't want to involve ROS in your data set collection, and then you could rerun that and actually inject that information through the ROS driver into the ROS system using these SVO files rather than taking live data or using a ROS back or something. So that actually is really nice. And then finally, dynamic reconfigure, so you can set all the parameters as you want at runtime, which is also always good to see that people are thinking about the actual how do we tune the system for user applications. So that is quite nice that is already involved. And yeah, I think that's pretty much all I had to say on this one. So this video, we installed ROS2 Humble from scratch, and then we made sure we could grab all the dependencies and work with the ROS2 driver for the ZED X camera so we could run that on bare metal. And yeah, then you're pretty much good to go to use this in any type of ROS2 application. So if you've got Move-It2 or Nav2 or something like that, you want to perform autonomous navigation or manipulation, you're pretty much good to go. Just set this topic and move forward. So these are using all the standard kind of interfaces like sensor messages, like the point clouds and IMU messages, and all that kind of good stuff. So there's really no difference at this point between these different messages and the other types of messages you might be using from a RealSense camera or something else. So it pretty much at this point is drop-in replaceable if you've followed through this part of the tutorial. So definitely stay tuned. So there's actually a new tutorial I'm working on for Nav2 to actually show how you integrate the VIO that's produced by these ZED X cameras into Nav2 in order to augment robot systems. So if you have like a tracked robot or like an Ackerman steering robot or a legged robot, these typically don't have very good odometry from just like the wheel encoders. So having a VIO solution augment that actually substantially improves the state estimation capabilities of those kind of like non-traditional vehicles, especially outdoor type environments. So I'm building out a tutorial in conjunction with Stereolabs, so we can show people how to actually leverage VIO to further improve their robot systems. And for that, I should have this whole kit set up on a robot, moving around a larger set of space. You can see that all in actual motion instead of on my little 2-foot cable in front of my desk. But yeah. Definitely make sure to stay tuned for that tutorial, and thanks for watching, and I hope that you're just excited as your new ZED camera as I am, and cheers.